Hello everyone and welcome back. So now that we've talked about how to find eigenvalues and eigenvectors, I want to talk a little bit about what they are used to do. And one of the applications, one of the neat real-world applications of eigenvectors and eigenvalues is that they can be used to predict the long-term behavior of a system that's evolving over time. So let me show you an example of that in action. So suppose that we have the zombie apocalypse happening, and we have a population of humans and a population of zombies. Let me use the subscript K to denote the number of months that have passed since the start of the zombie apocalypse, and let me use H sub K to represent the population of humans in that month, and let Z sub K represent the population of zombies in that month. Let's suppose that every month about 5% of the human population are bitten and transformed into zombies. And then we also suppose that we found a way to cure the zombies and that 10% of the zombies are cured and turned back into humans. Let's see if we can predict what's going to happen in the long run here. Are we going to end up curing everybody and everyone's human and the apocalypse is over? Are we going to end up with all zombies and all the humans are gone? Or is there going to be some kind of equilibrium or balance between the two states? Let's see if we can answer that question. So here's step one of that analysis. I'm going to start by taking this information about what happens to the population of humans and what happens to the population of zombies every month. And I'm going to turn this information into a system of recursive equations. One equation that tells us what's happening to the humans in the next month, and another equation that tells us what's happening to the zombies in the next month. So, for example, if I want to know what's going on with the human population next month, I need to first of all consider how many humans we are gaining as a result of the zombies that are being cured. Now, if we had Z sub k zombies in the previous month and 10% of those were cured, then zero point 0.1 times ZK would be contributing to the next month's human population. Similarly, the zombie population in the next month, Z sub k plus 1, that population would be increasing as a result of the humans that were transformed. So 5% of the previous month's human population was transformed and was turned into zombies. So that's contributing to the Z sub k plus 1 equation. Then we also have the zombies that were not cured. If 10% of the zombies were cured, then the other 90% were not cured. So 90% of the previous month's zombies are still around to contribute to the next month. And likewise, we have the humans that were not transformed into zombies. So 95% of the human population was not transformed into zombies and will contribute to the population in the subsequent month. So this system of equations tells us how the population of humans and zombies is evolving from one month to the next. In part two, I want to begin to bring a linear algebra perspective to this equation. And I want to think about the coefficients that are appearing in this system. Let's extract these coefficients and let's turn them into a matrix. The coefficient matrix for this system would be 0.95, 0.10, 0.05, and 0.90. And notice that this matrix here would fall into the category of matrices that we called a transition matrix back in lesson like 4. In lesson 4, when we were talking about matrices as used in real-world applications, we saw that you can use a matrix to store data about the probability of an object transitioning from one state to the next. And here we're seeing it for transition between the state of being human and the state of being a zombie. So now let's suppose that we have an initial population of humans, let's say around 100, and an initial population of zombies. Let's just say that there's a single zombie. If these are the initial populations, what calculations would need to be performed to figure out how the populations had evolved in 5 years' time. So our initial populations, which I might call H sub 0, Z sub 0, would be, based on the data provided, 101. If I wanted to figure out what was happening in month 1, I would have to take this initial state and I would have to multiply it by the transition matrix one time. So I would have A times 101, and that would give me what's happening in month 1. If I wanted to figure out what was happening in month number 2, I would have to take that H1Z1 and I would have to multiply it by the transition matrix again. Or in other words, I would have to take my initial state and I would have to multiply it by the transition matrix 2 times. 101 multiplied by 2 copies of A would tell me what's happening in the second month, and so on and so forth. If I wanted to know what was happening in the third month, I would need to multiply by 3 copies of the transition matrix A. If I wanted to know what was happening in 4 months, I would have to multiply by 4 copies of the transition matrix A. And if I wanted to know what was happening in 5 years, which is 60 months from now, it would require me to multiply by 60 copies of the transition matrix A. Now, no one really wants to be doing 60 copies of a matrix multiplication. So let's see if there's a more efficient way to get this calculation than to multiply by the matrix A 60 times. To that end, what we're going to do is we're going to examine the eigenvalues and the eigenvectors of this matrix A. Finding the eigenvalues of the matrix, let's go ahead and take my matrix and subtract lambda from the diagonal. So that 0.95 becomes 0.95 minus lambda, and that 0.9 becomes 0.9 minus lambda. Then we would find the determinant of this, and that would give us the characteristic polynomial. Which we would then set equal to 0 to find the eigenvalues. For the sake of time, and because these decimals are a bit messy, let's just do that on Wolfram Alpha. Okay, according to Wolfram Alpha, the characteristic polynomial of our matrix is lambda squared minus 1.85 lambda plus 0.85. And down below, under alternate forms, you can see this guy factored as lambda minus 1, lambda minus 0.85. So let's go ahead and write down the factored form. So now that we found the two eigenvalues of the matrix, let's go ahead and find their associated eigenvectors. So for example, focusing on lambda 1 equals 1, if I go into the matrix and subtract 1 from the diagonal entries, I end up with the matrix negative 0.5, positive 0.1, positive 0.5, and negative 0.1. And if I look at the null space of that, I can see right away that the second row is just going to vanish because it's a scalar multiple of the top row. So reading the first row, we get negative 0.5 x1 plus 0.1 x2 must equal 0, and then we have a free variable. x2 is free. So it looks like that forces x1 to be 2 copies of x2, and x2 would be itself. And so if I define a vector v1 to be 2, 1, then the associated eigenspace would just be the span of that. If I set lambda 2 equals 0.85 and I plug it into this matrix and subtract that entry from the diagonal, I get 0.10, 0.10, 0.05, and then another 0.05. So once again, if I think about the null space here, the second row is contributing nothing, and we get 0.10 x1 plus 0.10 x2 equals 0. x2 is free. And so that implies that x1 and x2 are opposites. x2 is equal to itself. And so we get our second major eigenvector here. The eigenvector v2 would be -1, 1, which means that the second eigenspace would just be everything that is spanned by that vector. But what I'm really focused on now is just this v2 itself. So we've now found the two eigenvalues of the matrix, and we found the associated two eigenvectors of the matrix. Now the question says, verify that these vectors span R2. Now, we already have two vectors, and that bodes well for the vectors spanning two-dimensional space. The only thing we need to make sure of is that none of the vectors are redundant. But visually, we can see that these two vectors are independent. There's no redundancy between them. In this case, neither one of them is a constant multiple of the other. So having two independent vectors, that is enough to span two-dimensional space. So in other words, importantly, every vector in R2 can be expressed as a linear combination every two-dimensional vector can be expressed as a combination of v1 and v2. So let's go ahead now and use these results to figure out what's going to happen to this population of zombies and humans in the long run. The first thing that I'm going to do is recognize that the initial state here, for example, H0, Z0 being 100, 1 is a two-dimensional vector. And since it is a two-dimensional vector, there is some way to express this guy as a combination of v1 and v2. So if I want to know what happens to this population in month number 1, we noted earlier that figuring out what happens to this population in month number 1 corresponds to multiplying that initial state vector by one copy of our transition matrix. But that's the same thing as multiplying this linear combination by one copy of our transition matrix. Now, if I distribute that A to each of the two eigenvectors, something really interesting happens, right? I get the appearance of this expression A times V1 and A times V2. And when you're dealing with eigenvectors and eigenvalues, a formation like that is really, really significant, right? Because the defining property of an eigenvector is that when you multiply an eigenvector by the matrix, what results from that is the same thing as that vector times its eigenvalue. So let's use this property here and replace A times V1 with the corresponding eigenvalue lambda 1 v1, and in the back, lambda 2 v2. So if I want to know what happens in month 1, I just have to multiply each of the eigenvectors by their respective eigenvalues a single time. If I want to know what happens in month number 2, corresponding to applying 2 copies of the matrix A, then I would just be multiplying the eigenvectors by 2 copies of the matrix A. And every time the eigenvectors are multiplied by A, they are scaled by a factor of lambda. So this would correspond to lambda squared times V. And in the back, the other lambda squared times V. And so on and so forth. If I wanted to see what happens to these vectors in month 60, corresponding to 5 years from now, that would be 60 copies of A times the initial state. That would correspond to 60 copies of A being multiplied by the eigenvectors. And every time the eigenvector is multiplied by A, we can rewrite that as being multiplied by its eigenvalue, 60 copies of lambda 1 times V1 and 60 copies of lambda 2 times V2. So let's go ahead and replace this abstract lambda 1 V1 and this abstract lambda 2 V2 with the specific values of lambda and V that we found earlier. Lambda 1 was equal to the number 1. V1 was equal to the vector 2, 1. And in the back, lambda 2 was equal to 0.85, and V2 was equal to negative 1, 1. Now let's think about this. When I raise 1 to any power, for example, 1 to the power 60, I just get 1 back. So this first term is just going to be C1 times 2, 1. And look at what's going on in the back. I have this value of 0.85 being raised to the 60th power. I have a number that's already small, and it's being raised to a very large power. And when you raise a small number to a very large power, the result is very, very small. So small as to be practically 0. So this term in the back will approach 0 as time goes on. So after a long period of time, our population of zombies and humans is leveling off to a certain ratio. Our population of humans after 60 months is some number times 2. Our population of zombies after 60 months is equal to that same number times 1. So what we can say is that after a long time, populations stabilize to a certain ratio twice as many humans as zombies. So we don't end up curing all the zombies, but neither do all the humans get infected. Over the course of time, we are leveling out and stabilizing to an equilibrium between the two populations, where the humans outnumber the zombies 2 to 1. So this is how eigenvalues and eigenvectors can be used to predict what's going on with a dynamic system like this that's evolving over time. We started by writing down a system of recursive relationships that showed us how the populations were evolving from one month to the next. Then we extracted the coefficients, we extracted the transition matrix for this system, and we found its eigenvalues and its eigenvectors. We noticed that the eigenvectors of this matrix span two-dimensional space. So in particular, our initial state our two-dimensional vector that told us how many humans and how many zombies we initially had, that initial state vector could be expressed as a combination of the eigenvectors v1 and v2. And because the initial state could be written as a combination of eigenvectors, it became very easy to see what the matrix A was doing to that vector over a long period of time. If, for example, we applied 60 copies of the matrix to the initial state, then that would correspond to applying 60 copies of the matrix A to the eigenvectors, which would cause 60 copies of the eigenvalues to appear. Here on GeoGebra, we can see the situation play out graphically. Here in green, this diagonal line represents the span of the eigenvector v1. This is that first eigenspace, all the eigenvectors corresponding to lambda 1. We started out with our initial condition here. Initially, we had 100 humans, which I've represented as 100 on the x-axis, and just a single zombie, so almost nothing on the vertical axis. I'm using the vertical axis to store how many zombies we had. Now, after 1 month, the number of humans has decreased and the number of zombies has increased. After 3 months, the number of humans has decreased further and the number of zombies has increased further. 10 months have passed, and now the number of humans is maybe around 70 or 71, 72. And as time goes on, we're seeing these state vectors begin to converge upon this straight line here. As more time passes, the population vector gets closer and closer to this eigenspace. And that reflects the fact that as time goes along, the populations are leveling out to have this ratio where the number of humans is double the number of zombies. The population is leveling out to eventually have this ratio. I had another example prepared, but this video is already getting a little bit long. So let me go ahead and just wrap it up. In this video, we studied dynamical systems, which are systems that are evolving over time. We saw how those systems can be represented using transition matrices and how the eigenvalues and eigenvectors of those matrices can be used to analyze what's happening to that system over a long period of time and to make that analysis pretty fast and pretty easy.